Okay, this is Unit 4, Practice Exam A for Math 1060. First question here is plotting a point that's given in polar coordinates. So remember when the r value is negative, you take 180 degrees from this angle, so 2 pi thirds. 180 degrees from that would be 5 pi thirds. And we go to the third circle here. For question 2a, this point given is in polar coordinates, so we need to convert it to rectangular coordinates. Rectangular coordinates has an x and a y value. So we need to find x, which is our cosine theta. We need to find y, which is our sine theta. So 4 times the cosine of 5 pi fourths. So this is going to be 4 times negative root 2 over 2. So now down here we get 4 times sine of 5 pi fourths, which is also 4 times negative root 2 over 2. So in rectangular coordinates, we have negative 2 square roots of 2 comma negative 2 square roots of 2. For part B, this point given is already in rectangular coordinates, so we need to convert it to polar coordinates. If you recall, there's an infinite number of polar coordinates that could work here. So to be specific, we want r value of 0 and theta between 0 and 2 pi. So r is equal to square root of x squared, which is negative 3/2 squared, and then y squared. So 3 root 3 over 2 squared. This becomes 9 times 3. This is 27 over 4. That's 36 fourths, which is 9. Square root of 9 is 3. And then theta, we're going to use an inverse tangent of y over x. And like I explained in class, I always take positive value of both y and x to ensure that I get an angle in the first quadrant, and then deciding which quadrant to be in based on where that angle or where that point is. So the 3/2 here are going to cancel. So this is the inverse tangent of the square root of 3. And that's equal to 60 degrees or pi thirds. Now, this is in quadrant 2. So pi thirds in quadrant 2 is 2 pi thirds, or the reference angle rather. If pi thirds is the reference angle, then that gives us an angle of 2 pi thirds. So the point in polar coordinates is 3, comma, 2 pi thirds. Question 3, part A, we're multiplying two complex numbers in polar form. Multiply the 3 and the 5, the modulus 3, the modulus 5, and multiply those together. And then we add the two arguments. One of them is 3 pi fourths plus pi 6. So 3 pi over 4 plus 1 pi over 6 is 11 pi over 12. And now we need to write that in rectangular form. Now, 11 pi twelfths is not one of the special angles on the unit circle, so I'm just going to estimate 11 pi twelfths. Cosine of 11 pi twelfths is roughly negative 0.966. And for sine, we do the sine of 11 pi twelfths. And that's 0.259. Then we multiply those both by 15. And for the cosine, that point negative 0.996 times 15, that's roughly negative 14.489. And for sine, that's 0.3882, or rather 3.882. Okay, question 3, part B. It's going to take us a little longer. Dividing the two complex numbers in their rectangular form. What was discussed and taught in class was to first convert both of those into polar form. So that's what we get to start with. Excuse me. So part B, the numerator here, we're going to convert this into polar form. So we need R. And we can simplify square root of 32 as 4 square root of 2. Now, the angle, we do the inverse tangent of 4 divided by 4 is going to be 1. So that's pi fourths. But 4 minus 4i is in quadrant 4. So in quadrant 4, we're going to turn that into 7 pi fourths. So 4 minus 4i turns into 4 square roots of 2 cosine plus I sine of 7 pi fourths. Now, negative 4 minus 2i, when you find the modulus, this is the square root of 16 plus 4, it's the square root of 20, and that's 2 square roots of 5. For the argument, do the inverse tangent of 2 divided by 4. And this is not one of these special angles on the unit circle, so inverse tangent of 1/2 in radians is roughly 0.464 radians. So that's in quadrant 1, but negative 4 minus 2i is in quadrant 3, so I need to add pi to this. Well, if we take 0.464 and add pi, we get 3.605 radians. So when we divide complex numbers, then when they're in polar form, we take the modulus divided by the modulus. That's going to be 4 square roots of 2 divided by 2 square roots of 5. That actually simplifies. Let's see, 2 square roots of 10 over 5. And then we subtract the two arguments, so 7 pi fourths minus 3.605. And that's 0.1893, or sorry, 1.893 radians. So now we need to convert this into rectangular coordinates. So it's this modulus times the cosine of the argument. That turns out to be negative 0.4. And then when we take this modulus and multiply it by the sine of this angle in radians, that comes out to be right around 1.2. So it's negative 0.4 plus 1.2i. Part C, we attack this similarly. We need to convert this complex number in rectangular form. We need to convert it to polar form. So modulus 9 plus 4 is 13. So the modulus is square root of 13. The angle or the argument is the inverse tangent of 2/3. Again, that's not an angle that we're going to find on the unit circle. So just need to estimate the inverse tangent of 2/3 to be 0.588 radians. Now that's in quadrant 1, and this complex number, negative 3 plus 2i, is in quadrant 2. So it's going to be pi minus this value. That's 2.554 radians. So in complex form, or polar form of this complex number rather, is square root of 13 times the cosine plus I sine, 2.554 radians. Now, if we're going to raise that to the 5th power, then we have the modulus raised to the 5th power times the cosine plus I sine of 5 times the argument. That's 12.768. Now again, we need to convert this back to rectangular coordinates. So it's going to be this modulus times the cosine of that angle, and that's 597. And then we're going to take this modulus times the sine of this angle, and that turns out to be 122. Or question 4, finding all the third roots. This is De Moivre's theorem. So the first thing we need to do is convert this complex number into polar form. So right now it could be thought of as 64 plus 0i. So then the modulus is 64, and the argument is 0 radians. So in polar form, it's 64 cosine plus I sine of 0. Now the third roots means z to the 1/3. So according to De Moivre's theorem, it's the r value, the 1/3, times cosine plus I sine. Then we have the argument divided by the number of roots. So third root means divided by 3, plus 2 pi divided by 3 times k, where k equals 0, 1, and 2. So for the first one, we're going to call it w sub 0. It'll be 64 to the 1/3 times cosine plus I sine of 0 divided by 3. And then if k is 0, this turns out to be 0. So it's 64 to the 1/3 times cosine plus I sine of 0. That turns out to be 4. For the next case, now for k equals 1, we're going to have 2 pi thirds times 1. So 64 to the 1/3 is 4. And then we can figure out the cosine and the sine of 2 pi thirds. So the cosine of 2 pi thirds is negative 1/2. And then the sine of 2 pi thirds is square root 3 over 2. So it's I root 3 over 2. And then for the third case, when k equals 2, so when k equals 2, we have 2 times 2 pi, which is 4 pi thirds. So now we can figure out the cosine and sine of 4 pi thirds. So cosine is negative 1/2. And for the sine, it's negative root 3 over 2. So it's so here we have the 3 third roots or cube roots, 64. So for part A, when we have the initial point and the terminal point of a vector, to find it in component form, we subtract terminal minus initial. And same thing here, terminal minus initial. And then for part B, we're going to find the magnitude. This is 549. And this simplifies to 3 square roots of 61. The direction and we can keep this in degrees. This is 39.81. Okay, so for question 6, we have the magnitude already. Magnitude is 5 units, and vector v lies in quadrant. Oh, it's a typo. That should be quadrant 3. Makes a 30-degree angle with the negative x-axis. So we can write this then, the x component of the vector is the magnitude times the cosine. So if it makes a 30-degree angle with the negative x-axis, that means the actual angle of the vector from the positive x-axis is 150 degrees. So this is going to be 5 times negative root 3 over 2. This is going to be 5 times 1/2. So as a linear combination, it's going to be negative 5 root 3 over 2 I plus 5/2 j. So for question 7, we just need to multiply vector A by 2. So that's going to be 4 comma 6. And then vector V by 4 is going to be negative 12 comma 20. So when we add them together, we add the horizontal components together. So that's going to be negative 8. And we add the vertical components together. It's going to be 26. So now for part B, find the angle between the two vectors. They're referencing vector A and V right there. So the vector between the two angles was a function of the dot product. So if you recall from section 7.3, the cosine of the angle between the two vectors is the ratio of the dot product of the two vectors divided by the product of the two magnitudes. So first thing we need to find is the dot product. So V dot product of V and A. So vector V is negative 3 comma 5. Vector A is 2 comma 3. So the dot product is that linear combination, product of the two horizontal components plus the product of the two vertical components. And then the magnitude of V is the square root of 34. The magnitude of A is the square root of 13. So then cosine of the angle between the two vectors is equal to the dot product, which is 9, divided by the product of the magnitudes. That ratio comes out to be about 0.428. So the inverse cosine on both sides gives us an approximate value here of 64.65 degrees. Question 8. We have a boat that leaves a port and it's fighting against a current with a bearing of 60 degrees east of north. Find the true speed and the bearing. So this would be an application of adding two vectors together to find a resultant vector. So if we were to draw this out, the ship leaves with the initial vector of 20 degrees south, or 20 degrees east of south. and it's a magnitude of 42 miles per hour. The current of the ocean is 60 degrees east of north. The magnitude of 5 miles per hour. So really what we're trying to get here is if we were to translate that vector down here, we need this resultant vector. So we need the angle, the bearing there, and the magnitude of that vector. So we need to find the component form of the ship vector and the component form of the current. So the magnitude is 42 miles per hour. So for the x component, we're going to do 42 times the cosine of the angle. So here, if this is a 20-degree angle, that means this is a 70-degree angle here. And since it's in the fourth quadrant, we're going to go -70. For the y component, the vertical component, we can do sine. This is about 14.365. And this is -39.467. Now for the current vector, magnitude is 5. And the bearing here is 60 degrees east of north. So that's 30 degrees from the horizontal. So that's cosine of 30. Or how 4.33. And then for the vertical component there is 5 times the sine of 30. So if we add these two together to get the resultant vector, we add the horizontal components. That's going to be 14.365 plus 4.33. And that's 18.695. And if we add the vertical components, we're going to get -39.96 or -36. So if we find the magnitude there, that comes out to be about 41 miles per hour. It says round to the nearest mile per hour, so that's 41 miles per hour. Now the direction, which is again different than bearing, but the direction is the inverse tangent of the y value. I'm going to make it positive divided by the x value. That's 63.13. Now in quadrant 4, I'm going to make it negative. So then the bearing would be the complement of that, the distance from the vertical axis, which is 90 minus that. Which is 26. It wants us to round to the 10th, so 26.8. So that would be south 26.8 degrees east. So there's the true speed of the boat, and that's the true bearing. So what we got here is if the angle to that bearing is 63.3, then the complement would be the bearing here. So if this was 63.1, then from the vertical axis, it's 26.8, roughly. Okay, question 9. We have a box, and it's going to be lifted 10 feet off the ground, so it's ground level, and it's 25 pounds. The only force acting against it is gravity pulling it down, so gravity's pulling it this way down. So in order to lift it up, we need a force this way of 25 pounds. So we need a force of 25 pounds that's in the same direction as the displacement vector. So work is equal to the dot product of the force vector and the dot product of the displacement vector. So the force vector, 0 in the horizontal, but 25 in the vertical, and the displacement vector is again 0 in the horizontal, but 10 in the vertical. So the dot product is equal to the linear combination, the product of the horizontal components, plus the product of the vertical components. So it takes 250 foot-pounds of work.